So welcome to lecture number 20. Now, so we said last time we were talking about this kind of things, commutativity. Now we can define this as, let's say, AH minus HA equal to, let's say, I give a notation AH. So now AH is equal to, let's say, minus HA. It means it is not commutative, right? If we allow this definition, so it is not commutative. They are different. This operator acting on this minus this operator acting on this, it is not always equal. They could be different, right? So this structure can help us to study interaction between operators. Is it commutative? Is it associativity? Is it closure? Right? Does it have identity? Does it have inverse? And so on. Right? Now let's see an example. So we have G, H, some O operation where O is defined as G cross H2, let's say G for this time. Now say we have set of G. The set of G is, let's say, an operator dy dx. Okay, and let's say we have a set. I don't want to close this right now. We will see why. Let's say H is some operator integration, this operator, right? Now, so we have two different kind of operator, set of operator. Now this, what is O is going to take? It is O is going to take G cross H to G. Now, so it means G is our dy dx and this is cross, so it will form an order pair, and this is going to produce dy dx O, operator O acting on this. So we get dy dx of this dx, right? Now these two things, it must belongs to G to satisfy closure property. Now, does this belongs to G? Well, it does not, right? So maybe we should keep this here, right? We can put this into this set. But then how far we can expand, that is the problem, right? So maybe we can solve this problem by redefining what this integration is, and we can do it by using a notion of fractional calculus. The idea of fractional calculus is you can compute dy dx with negative power, right? With negative power, and this is exactly what integration is. Okay, so now we're gonna make our this set in different way, which is G equal to, we have dy dx and H equal to this set, because this is now integration. So now what happens? O, so G cross H to G, it means O is going to take dy dx and d inverse of dx inverse, right? And it is going to produce dy dx acting on d inverse and dx inverse. So what does it produce? So it will give dy dx of d inverse of dx inverse. So what is the answer for this? Well, we know from algebra, the algebra of calculus, that d power m by dxm and d power n by dxn is exactly equal to dm plus n by dxm plus n. And we can use this property here. So what we have got is, so let me take this value and put it here. So we have dy dx acting on this. So we get d 1 minus 1 and 1 minus 1, which is d0 by dx0. It means it's zero order derivative. So it produces nothing. It produces just our function f of x. So now does f of x belongs to our g? Well, no. It is only dy dx. So it means we have to put f of x into this? Well, not really, because this is set of operator, not set of function. We cannot put function in the set g. So maybe we can do here, which is dy dx. We can do not dy dx, let's say alpha dx alpha. This is our set now, where alpha belongs to real number. Now, so our output was d0 by dx0. Now, does this belongs to the set g? Well, yes, because alpha is 0 and 0 belongs to real number. So if we keep 0 here, we get this set, right? I don't know if I'm making clear. Let's make it clear now. So what we are saying, that we have set g and this is dy dx, and we have set h, which is integration of dx, and then we have operation which is g cross h to g, right? Now we said use of fractional calculus, we said this integration of dx is defined as dy dx of inverse, right, with negative 1 order derivative. So we can extend this set, and the extension of this set will be h equal to d inverse dx inverse, right? Now so this set has this operator, right, and this set has this operator. But then we said O is going to do what? It is going to take this both operator from different set, and it is going to produce dy dx acting on d inverse of dx, and by use of algebra we can say this is this, and this produces dy dx of 1 minus 1, and from here we get d0 by dx naught. So but here we have power 1 and here we have power 0, so it does not belong to our set g. We can see here this does not belong to set g. Now if it does not belong to set g, it means it is not closure. So how can we make it close? Well, we can make it close if we assume this value is in our set dy dx. So if this is d naught by dx naught is in our set, then we can say it is closed, right? So we have two different things. So now we can generalize our set. The set is g, and this set is d alpha by dx alpha, and maybe I should put this way. So our set will be now g equal to d alpha by dx alpha, such that this alpha equal to 0 and 1. So this is our first set, right? This is a set of an operator, and then we can have a different set. What about h? H was this integration dx. It is a set. Now we can extend this, and we said this can be redefined another set which is d minus alpha and dx minus alpha, such that this alpha equal to 1. So we have this H, this set, and then we have this set. We have two different sets, right? So it is closed now, right? Is it closed? Well, it is closed. We can check that. So now if we expand this set, we can see here, right? Maybe let's do it here. So we have this set. We are going to check closure for this set GH, O. This is our algebraic structure where O is defined G cross H to G, and we have the set G equal to D alpha upon dx alpha, such that alpha equal to 0, 1, and then we have set D minus alpha dx minus alpha where alpha equal to 1. So if we expand this set, we get d by dx and d naught by dx naught, and here we get d inverse dx inverse, right? Now we can check closure, and to check closure we use Kelly table. So here is our operation, here is our G set, and Kelly table is, we know what Kelly table is. We have to put this value top of here, the set of G, the element of set G will be here. So the element of set G is this and this, so right, and the element of H will be here, which is just 1, this one. So we can substitute this. Now we can check a closure property, which is this time this. For the closure property, what we want is not this time this, right? Because closure, it means, see here, what is going on here? G acting on H, not H acting on G. It is opposite. But here, this is H and this is G. So here, right now here, H is acting on G, and we don't want that. We want G acting on H. G acting on H. So it means we have to reconstruct the table, not this way. The table will be this. The element here will act on this element. So it must be H. So it must be G. So G is our two element, d by dx and d inverse, d naught and dx naught. These are the element of G. We saw here. These are the element of G. So these are the element of G. Now here will be set H. Now what is the element of H? Well, here it is, d inverse dx inverse. So we will substitute this d inverse upon dx inverse, right? Now we construct the table. So d by dx, and this is the operation. So d by dx acting on this. So what will be the answer? Well, d by dx acting on d inverse dx inverse, which will be equal to d by dx acting on dx inverse, which is equal to d naught upon dx naught, right? And this belongs to G here. So the first closure is satisfied. Now for the next element, we have d naught upon d naught x naught acting on d inverse upon dx inverse, right? So what will be the answer? Well, we have to calculate it, and we can see d naught acting on d inverse dx inverse. So answer will be d inverse dx inverse. Now does it belongs to G? Check here. Well, it does not. Here is no. This element does not belongs to set G. Now, so this does not belongs to this set G. We said it, right? So now it means this structure with this set fails to, you can say it fails to satisfy closureness. So it is not even a magma, right? It is not an algebraic structure. It is not even an algebraic structure, you can say it. With this kind of operation, it is not an algebraic structure, right? Now, so it does not, well, it does not mean this will never be. We have to check it, right? Maybe we can find some kind of set where this happens, this kind of a structure. For now, with this example, it is not even closureness. Forget about other property, right? Maybe if it fails closure, then we cannot talk about anything else. That is simply talking about associativity, and other will be simply meaningless, right? Now last time we saw, now if we change the definition, as we said, we had two options, which is this and which is this. Here star goes from G cross H to G, here star goes from G cross H to H. We saw this structure with that set didn't satisfy even closureness, it failed. With this example, we can see if it satisfies other property of axioms. Maybe we can define a set G will be set of some operator. So let's say we have some operator dy dx. Let's say H is we have a set, and here is our another set. Now what is this star gonna do? Star is going to do this. It's going to G cross H and going to produce H. So let's check it if it satisfies closureness. So to closureness, we are gonna make this Kelly table. Here is operation, here is G acting on H. So G element is d by dx. So we substitute d by dx. Here are 1, 2, 3, 4 element. 1, 2, 3, 4 element. Right? The first element will be what is the first element? The first element is of set x, h, x square, then 2x, then 2, then 0. Now let's act on this. So d by dx of x square, the answer will be 2x. Here d by dx acting on 2x, answer will be 2. Here d by dx acting on 2, the answer will be 0. Here d by dx acting on 0, answer will be 0. These all element, all of this, these all belongs to our set H. We can see it, 2x is in the set here, 2 here, 0 here, 0 here. So it satisfies closure property, right? Now we are gonna check associativity, and for associativity we need minimum 3 element A, B, C coming from G. But here we have only 1 element. So now let's extend this idea, and we keep 3 element here. So we extend this and say G has 3 element, which is d by dx, another is dx square by dx square, and another is an operator identity, which is going to do nothing. Now this will act on this set. Now we are going to check if it satisfies associativity or not. So we have the set G, which is first is no derivative, there is first derivative, and there is second derivative, right? Let's say there is one more, the fourth cube derivative. And then we have set H. Let's say we have x4, 4x cube, 12x square, then let's say 24x we have, then we have 24, then we have 0. This is the set of element, and the star is defined G cross H to H. Now we are going to check all those operations, associativity and all, in the next video.